Impatience is a virtue. My name is Sam Goff, and I'm a senior engineer at HPE, where I lead UI development for Green Lake Bare Metal team. I've worked on enterprise apps and e-commerce sites. I've focused on real-time data, security, and accessibility, but my real passion is for performance optimization. So, what's the big deal? Why is performance optimization so important to me? Well, in my experience, we always think we'll have more time to do something important until we don't. When I was 17, I was in a head-on collision with a semi-truck at highway speeds. I was able to walk away from that experience, but it gave me kind of a new perspective on life. It was sort of a shakabuku moment, as they would say. It really puts into perspective what's important in life. I feel incredibly fortunate because I haven't just walked away from one major car accident. I actually walked away from 8 major car accidents. Every single one of them could have turned out very differently, but every single time I found myself very powerfully reminded that every moment is precious and you have no guarantees that there will be more of them. So as developers, we can have a powerful impact on hundreds of thousands or even millions of users. So if we can make our app or our website radically faster, not just a few percentage points faster, but 10, 20, 100, 200 or more times faster, if we can do that for our users, imagine all of those moments we can give them back. To paraphrase Mark Rober, the beautiful thing about being an engineer is that when you see something in the world that you aren't happy with, you can invent a way to make it better. So for that reason, I think impatience is a virtue. So this is how I discovered Next.js. In my previous life, I was a professional photographer, among other things. And I was creating high dynamic range images before all the cool kids were doing it. I even wrote some software that made it easier to create some HDR panoramics 20 plus years ago. So I've always been struck with the Sophie's choice that we're put in. You can have either image quality or speed, but you can never have both. So I obsessively profiled different file formats with different encodings, various noise reduction and other pre-processing techniques, and I figured out how to produce the best image quality with the smallest file size for various types of images. So what I've found is that images are often the pain point for web and app performance, and they also provide a tremendous opportunity for massive improvement in performance with a fairly achievable set of techniques. At various roles, I've built image processing, optimization, and CDN pipelines. I've also implemented lazy loading on the client side with a responsive image component that I built in React at multiple roles. And I took advantage of this new thing back in the day called source set and sizes, which everybody knows about these days, but back in the day it was brand new and it was just gained enough adoption among all the different browsers that we could actually utilize this capability along with some polyfills for all of the other browsers that were still in use and lagging behind. So at one role, I was able to achieve some pretty amazing performance. The file sizes were 85 to 95% smaller and uncompromising image quality and color accuracy. At another role, I discovered we were not applying any optimization to user-provided images. The problem with this is if it's possible for your users to do something, they will eventually. And so if it's possible for a user to upload a 25 megabyte JPEG, it will happen sooner or later. And in our case, it wasn't just 1 or 2 users, it was legions of them. uploading images that were way larger than they needed to be. You could give them guidelines, but again, if it's possible for them to completely ignore those guidelines, it often happens. And so we had our app displaying hundreds of thumbnail images, each of which could be several megabytes in size. And so the app was slowing to a crawl. It could take 3 to 5 minutes to just load a single page. And I'm talking about just the above the fold content, because there was no lazy loading of the images and there was no particular sequence in which they were loading. So images, hundreds of images down from the top, were loading and blocking and preventing the above the fold content from actually loading. So in that situation, I was able to add lazy loading, image optimization, CDNing, and responsive image loading using source set and sizes, and I was able to improve performance by over 240 times in one afternoon. So after I left that role, I started to think, maybe I have something to offer, because if it's accessible to enough people and it's easy to implement, I might be able to make it into a service, or maybe just a really smart component, a little library that people go beep, and all of a sudden their app is faster because they're using really smart loading techniques. And they're also able to easily add image optimization, lazy loading, all the other buzzwords in basically a few lines of code. So I did some research, and as I was in the process of starting to build this, I discovered that there was this thing called Next.js, and they had this image optimization component, and they had made a lot of the same implementation decisions that I had. And I was kind of blown away with just how similar our approaches were. And so that led me to do more investigation into Next.js as a framework. And I started to realize, you know what? If I were to build a framework, I probably would have built it exactly like this. I love all of the decisions that they've made, and they obsess about performance the same way that I do. And they rightly have identified image optimization as one of the huge opportunities for performance improvement across the web and across apps. And in my opinion, they've made it really accessible by turning it into a simple image component that anyone can learn to use and get great results in a very short amount of time. So, aside from obsessing about image performance, I'd like to take a step back and talk about how I think about performance. So, from my perspective, I like to measure what matters, prioritize what matters, and then challenge all assumptions. So, what does this break down to? So when you measure what matters, you're deciding where to draw a box around the problem. So when you draw a box around the performance of your app or website, you might decide to draw a box around all the things, measure all the things. This would be the classic waterfall approach. Initially, this can give you a really good perspective on where some of your problems might be, depending on what those problems are. But ultimately, your goal is going to be to move everything to the left of your waterfall as much as possible, and also reduce the number of things in your waterfall. Core Web Vitals is a much more recent way of looking at things, and it also focuses more on the perceptual aspect of performance. How does your user perceive how quickly things are loading, and how does the user perceive the performance of your app, and how quickly can they interact with it? So as you're trying to decide how and where to measure performance in your app or website, you may discover that there are just so many different issues, and it basically looks like noise because there are so many different things that are going on all at once, and they're basically making it difficult to isolate where the problem is. Well, if you have enough problems to start with, this can kind of confuse the picture. So a big part of what I've spent my career doing is stepping into teams, inheriting a code base and then looking around and figuring out where the bodies are buried in the code and in the actual system implementation. So this is where you get to start prioritizing what matters. So I've found that it's really helpful to take a variety of approaches. One is to look for the low-hanging fruit. You try to identify situations where it would be very easy for you to make a big improvement. Coming at it from another angle, you can look for situations where you can make a massive leap forward in performance. It might require a little bit more time and energy, but you know that the gains will be massive. And then there's the 80-20 rule. You're looking for situations that impact either the largest number of users or something that happens very frequently. And then finally, challenge all assumptions. And here's the hard part. Stepping outside of yourself and recognizing all of the assumptions you've already made or that have been made by others that have come before you. And the challenge is to articulate these assumptions and document them. So for example, one assumption I could point to is that as developers, we tend to assume that everybody else has fast internet, like gigabit internet, just like me. Well, as you'll discover, that is not always the case. We are not our users. So what makes apps slow? This can include the number of round trips that need to happen, meaning requests that get fired off from the user's device to wherever it's trying to get the data and come back. Every single time that it travels from client to server and back is a round trip. And that server could be in an AWS data center on the East Coast or West Coast. It could be a Cloudflare server on the edge. It could be a data center in Iowa. It just completely depends on the situation. When you're waiting for data to travel from one place to another on the internet, this is latency. That's impacted by how far it has to travel and the topology of the network. What protocols are being used has a tremendous impact on performance. The encoding or compression being applied, the size and number of files, transforms that need to occur to the data along the way, optimization or lack thereof, polling, and finally, there's waiting until the user makes a request before you fetch the data they're asking for. As Benjamin Franklin said, an ounce of prevention is worth a pound of cure. So when it comes to round trips, 85 to 90% of time spent waiting for an app or website is from network requests. The more network requests you have, the slower the app will load and operate. In years past, browsers could only make up to 6 connections per domain simultaneously. Now, in more recent years, that's gone up depending on the browser. You can sometimes get anywhere from 2 all the way up to 17 connections per domain now. But still, it's a constraint. If you have a lot of connections going out, it's going to slow down your app. So latency. This includes DNS lookup, queuing the request, TLS negotiation, transmitting the request, waiting for the server response, and then downloading the response. So when you think about it, latency is actually a multiplier against the number of connections or round trips that you have to make. So when it comes to distance or network topology, electrons travel just below the speed of light. So the farther that data has to travel, the longer it takes. So if you think about it, if you're loading something that's already in your browser's memory, that's about as fast as you can get. Step slower than that is having to read it off a disk or SSD. That's called the browser's cache, right? Further out, you get to an edge server, but it's still pretty darn close. It could be just a few miles away or a CDN. Further than that, it could be a data center a few states away or half a continent away. And then of course, once you're in the data center, you've got servers and databases, but every single hop the data needs to make takes longer because it has to travel further and it has to go through more devices along the way. So when you think about it, requests for data double the latency because it has to travel both directions. Or put another way, server push can actually have this latency because it only has to travel essentially one direction. So protocol, we're talking HTTP 1.1, which has been around for decades, HTTP 2 or H2 for short, or HTTP 3, which is the new kid on the block. But it's not yet the default on all browsers. So with HTTP 1.1, you're basically limited to only one request per TCP connection. And this is a problem because the more HTTP 1.1 connections you have, the more HTTP 2 connections that you're blocking. So with H2, we have multiplexing, which allows the browser to negotiate a single TLS handshake, and then once it opens up a channel of communication, it can reuse that channel of communication to send multiple files across that channel. That's multiplexing. You can also add server push, where the server proactively says, you know what? I know that you're going to need this, so I'm going to go ahead and send this to you before you even ask for it. Another big win for H2 is the ability to add header compression. And when you do this, you're able to radically reduce the cost of TLS connections and the additional information that's sent over the header. H3 runs over quick and it produces a much faster TLS handshake. This is coming in the near future to more browsers, but it's not yet universally out there. So for the most part, your safest option is HTTP 2 because it's universally supported and it produces much faster connections. And so this is a perfect situation to challenge assumptions. You know, a lot of people assume, oh, well, HTTP 2 is the modern standard. All of the connections in my app have to be using HTTP 2. I think you'd be surprised. Open up your waterfall. By default, Chrome and other browsers do not necessarily show you what your protocol is. Make sure you turn it on, and when you do, I think what you'll be horrified to discover, there are actually connections that are not using HTTP 2. And so if they're using HTTP 1.1, the scary thing about this is a very small number of HTTP 1.1 connections can block a very large number of HTTP 2 connections that could be multiplexing and efficiently utilizing those channels of communication. And so it has a disproportionately hobbling effect on the performance of your app. Another important aspect of performance has to do with encoding or compression, because it has a profound effect on the file sizes being transferred over the network. In general, larger files take longer to transfer over the internet than smaller files. Uncompressed data is typically 200% to 900% larger than compressed data. gzip is a universal standard. Every browser on the planet has it. gzip is typically 15 to 50% smaller file size. Brotli is a newer technology, and it can produce file sizes up to 90% smaller. At this point, all of the major cloud providers offer Brotli, so why not use it? So there's another opportunity to challenge an assumption. A lot of people probably assume, well, all my data is efficiently encoded. Who wouldn't use Brotli? Or let's put it another way, a lot of developers probably assume that their data is already being provided to them encoded, compressed using either gzip or Brotli. At the very least, gzip should be used, but you can always take existing gzip encoded data and get additional gains by re-encoding it with Brotli. So there's an assumption we can challenge here. We might assume that all of our data feeds are being efficiently encoded. You might be horrified to discover that not everybody is using the best practices here. Some APIs, some backends prefer to party like it's 1999. They actually don't even use encoding whatsoever. So the takeaway here is if you inspect your waterfall, turn on encoding. And what you'll discover is either it'll say gzip or br for Brotli, or it might be completely blank. And if it's blank and it's a static file, JavaScript, CSS especially, or JSON, and you discover that some of those files are not being encoded, that's a huge opportunity for performance improvement. All other things being equal, transmitting a Brotli encoded file 1/10 of the original size happens 10 times faster. So image file size and performance is one particular area that is low-hanging fruit, because you don't have to load all the images on an app or a web page in order for it to look good for the user. All you have to do is load the above the fold content efficiently. This technique is called lazy loading, and this is one of the many things that Next.js did really, really well with their built-in image component. Image optimization gives you an optimal native image size in terms of the number of pixels. Optimal file format and encoding is another opportunity. And then, of course, when we're talking about logos or things that would lend themselves well toward vector art, you'll find that SVG is ideal in many of those cases. Generally speaking, when you have raster-based images, JPEGs, PNGs, WebPs, and others, these should be served up with responsive images using source set and sizes. Yet again, this is a situation where Next.js really makes it quite accessible, very easy to use. And then finally, you want to CDN your images. So this is another opportunity to challenge an assumption. A lot of people might come into a role, look at an app or look at a website and go, oh, well, of course all the images are optimized. Or you might come into a situation where you have zero control over the user provided URLs to these images. So the assumption in that situation might be, well, we have no way to add image optimization. We have zero control over this data feed. So this is another assumption that should probably be challenged, because it's a big one. Well, the good news is it's become easier than ever to actually do that. So for example, Next.js alone, just using the right image component, can make it very easy to add responsive images that are optimized at build time. If you have dynamic image sources, such as an external data feed of user-provided images that's always changing, you can add something like Vercel or Cloudinary. You can actually add runtime optimization, where when you make the request the first time, it provides the optimization, and then it caches that and CDNs it, and then any subsequent requests are actually already optimized and they're already in the CDN. So adding image optimization has become very accessible and very affordable within the last several years. So a lot of times our apps or websites rely on data feeds. And a lot of times we don't have a lot of control over how optimal the data is for how we intend to use it. It varies in quality, and the situation that we deal with in the enterprise is quite often we have a lot of REST endpoints. And quite often the people who are creating these REST endpoints care more about the back-end performance than the people who are actually consuming it, especially if there's a GUI involved. So what you may find is that you just have to deal with it. So in recent years, GraphQL has become an extremely popular technique for dealing with less than ideal APIs and endpoints, where data has not been optimized for front-end rendering and interaction. So the advantage of REST is that it's fast, it's easy, it's universally understood, but quite often we find that it's just not optimal for presentation or interaction. In one app that I've worked on, I discovered that one single view requires 19 separate REST endpoint calls. And then the UI has to essentially accomplish various transforms. It amounts to effectively a client-side join, which is quite possibly the worst possible way to architect an app. So this is something that in the real world we end up having to deal with from time to time, sometimes all the time. So a solution that's kind of come to the fore within the last several years has been GraphQL. It's been wildly popular because it allows UI developers to really easily make transformations to optimize for rendering, presentation, and interaction. So this can be used as a mediation layer between client and existing REST endpoints. It's fast and easy to implement and easily iterate and improve upon. You can combine multiple different endpoints into a single optimized data feed, and you can even add caching at this layer. However, there are some drawbacks. GraphQL queries can expose a very large attack surface. And so it's recommended that you move those queries to the server side in prod and integration environments. Additionally, with GraphQL, nested resolvers can cause a cascade of REST calls. So the end result is that you end up with a lot more REST traffic on your backend resources than you would if you had just crafted a single well-architected endpoint. So another beautiful thing about Next.js is the addition of middleware and edge functions, where you can easily add all kinds of presentation-specific transformations to your data feeds, and you can optimize it for presentation and interaction. So when you're sending data down the wire to the client, the only data that you need to send it is what's actually needed to render and interact with. So in addition to only including the data you actually need, you can add Brotli encoding in middleware and edge functions. And so the resulting file size can be even smaller than 1/10 of the original file size. And having deployed multiple projects with Vercel, this is just automatic. You don't even have to think about it. You don't have to opt in to Brotli encoding. It's just done for you. The best practice is just already applied. If you put middleware or edge functions between your client and existing REST resources on the back end, the beauty of that solution is you can guarantee there will be no more REST endpoint calls to the back end than what you currently have. The game changer, though, is that your front end performance is night and day different. When your data feed is 1/10 of the original file size, generally speaking, your app performance will be roughly 10 times faster. If you're moving your data from a data center half a continent away to an edge server just a few miles away, your latency is going to be vastly reduced as well. If you add caching on top of that, or if you incrementally generate updated content based on dynamic data, you can vastly improve the performance of your app or your website. I've personally tried this with real-world apps, and anywhere from 7 to 20 times faster is the actual measured outcome that I've had. There's one more opportunity for a massive leap forward in performance. When you stop waiting for the user to ask for the data, when the system of record knows the data has changed, you can push the data toward the user where they can then consume it more quickly because it doesn't have to travel as far. If the system of record knows what data is important to certain users and it basically maps those dependencies. So when the system of record changes, and it changes something that users care about, it can stream those changes to a cache. It can, with very fine granularity, invalidate just the part of the cache that we know is no longer current, and then stream those changes to update the cache. Here's the interesting thing. With Next.js, middleware, edge functions, and the various rendering techniques, you have ISR, incremental static revalidation. So if you think about it, if you can switch from polling to streaming, and the streaming can push the data into a cache, you can set up ISR using Next.js to consume the result of that streamed data. And it can incrementally regenerate your static content. It's static because it's an HTML page or an HTML component, but the beauty of that is you are no longer waiting for the user to make a request and then firing off that request that has to travel all the way back to the system of record, because the system of record has already pushed that content, that new data, to the edge. And it can be rendered at the edge, and it can be cached at the edge. So the beauty of this technique is that you can push the data as close to the user as possible, and then when the user goes to make the request, the data is already there and it's in a format that is optimal for their consumption. And as we know, React is working on server components where it can efficiently render just the component that has changed and then stream those changes efficiently over the pipe from the edge to your client. And the beauty of that combined with ISR is that you can push your data from your system of record to the edge, revalidate, and then stream only the changes to the HTML to your client. What I've just described is a complete inversion of how things have been done in the past. And if you can wire up all of these different connections to stream changes in data all the way to the client in real time, you can end up with massive performance improvements. And at the same time, you can actually ameliorate your back-end resources significantly. In one example, we identified that 99% of database activity was read-only. So in 1% of the situation, the data changed. The other 99% of the time, this was an opportunity for introducing caching, because if you can point the request to a cache because you know that nothing has changed, all of a sudden 99% of your database operations can go away. So in general, polling is the least efficient way to get data. And it only occurs because we have no way to know whether the current version of a resource is fresh or stale. So, what makes apps slow? If I had to boil it down to just a few things, first of all, it's doing unnecessary work. Really what it comes down to is ignorance. We don't have enough information. Has our data changed? We don't know. So when it comes to databases, the fastest DB operations are the ones we can prevent. If you think about it, the more DB ops we can prevent, the faster and more scalable the system becomes. So to sum up, how I think about performance: measure what matters, prioritize what matters, and challenge all assumptions. What does this translate to? Well, in actuality, you end up looking at the waterfall. You look to reduce your round trips as much as possible. You look to reduce your latency, and you try to reduce the distance data has to travel when the user is asking for it. What this ends up meaning is that your data needs to get pushed as close to the user as possible. Typically, this is at the edge. This also means using H2 or H3 instead of HTTP 1.1. This means using Brotli encoding wherever possible. Minimizing file sizes being transferred over the wire. Optimize CDN and responsively fetch images. Optimize data feeds for use. Replace polling with streaming wherever possible. Cache as close to the consumer as possible, which again is the edge. And then finally, stop waiting for the request from the consumer. Be proactive about pushing the data to where you know it's going to be needed. So hopefully by now, I've convinced you that impatience is a virtue. I encourage you to be impatient and make the web faster.